In this lecture, we'll be looking at using a Raspberry Pi as a digital signal generator. To follow along, you'll need a Raspberry Pi, a microSD card, and a means of reading and writing to the microSD card. The Raspberry Pi is a small form factor computer that features general purpose input-output or GPIO pins. Using Python, GPIO can be programmed to output 3.3 volt DC current. Unlike some Arduino boards, the Raspberry Pi does not have any analog output pins. However, you can get DAC hats, which are modules that fit on top of the GPIO pin rack to produce analog currents. All models of Raspberry Pi have the same GPIO pins, although sometimes the numbering is different. The Raspberry Pi that I'll be using for this is the Raspberry Pi 0WH. The 0WH has a very small form factor, being smaller than a credit card. It's powered by a micro USB power connector similar to a phone. It supports wireless internet, unlike the standard Pi Zero, and it has pre-soldered header pins. It's also incredibly cheap to get hold of one of these, at them costing less than £15 per unit. To control the Raspberry Pi, we'll be operating on it remotely using a secure shell or an SSH connection through the local area network. On Windows, you'll need to install the software PuTTY to log into a remote device using SSH, and on all computers, you'll need to install Nmap to find the Raspberry Pi on the local area network, and you'll need to install the Raspberry Pi Imager software to write an operating system onto a microSD card to boot the Raspberry Pi in the first place. To install the Raspbian operating system onto the Raspberry Pi, you first need to insert the microSD card into your computer through an adapter or through a dedicated microSD card port. Once in the Raspberry Pi Imager software, select Raspberry Pi Oz Lite and choose the SD card that you've inserted into your computer as a storage medium. We're using a 16GB microSD card here, but a smaller one should also be fine. Then press write, enter a password if needed, and then wait for the write to finish. This process will split the SD card into two separate partitions, a boot partition and a root file system partition. Inside the boot partition, we can create two files, one for SSH and one for the Wi-Fi, to configure them prior to booting the Raspberry Pi. To do this, insert the microSD card into your computer again, and open the boot partition of the two partitions available. Then create a new empty file called SSH with no extension, and create a file called wpa-supplicant.conf, which we will then edit to put in the network details. Now the WPA supplicant file needs to be set up. First, you need to set the country, as different countries use different bands, so it needs to be set correctly. And then you need to set update config to 1, so that the WPA command line interface will be able to update the appropriate config file. Then, the control interface path needs to be set as to where the config file will be stored once it's fully loaded. In this case, we'll be using var run WPA supplicant. Now you need to create a new network object to store the details of the Wi-Fi that you want to connect to. So we'll set scan SSID to 1 so that it can find hidden networks if necessary. We'll set the SSID, which is the name of the network, and then we'll set the password, or as the PSK, which is the password to connect to the network with. Then make sure you save the file, and it should be good to go. Then, remove the microSD card from your computer and insert it into the Raspberry Pi Zero. Connect it to a suitable power supply, and the green light should turn on and begin to blink. It may take a few minutes to do the initial startup and then to boot. To log in, we need to check the local area network for the Raspberry Pi's local IP address. First, we'll be using ifconfig to find the local IP mask. Then, with the local IP mask, we can use Nmap to scan the local area network for the Raspberry Pi. We can pipe the output of Nmap through grep to filter it for Raspberry Pi devices. Also note that the Nmap command is run with sudo or with superuser privileges. This is because without sudo, Nmap cannot access the MAC addresses of devices, which means it cannot determine what type of device is at the IP address. So let's run through how to do this quickly. So the first command is ifconfig, and we can see here that on our main network device, not the loopback device, that our local IP address is this 192.168.4.92. So I'm going to copy that and then do mmap-sn, which is for a ping scan. And then we're going to remove the 92 from the end and place a star to scan across the entire range here. And then we press enter on this. And then it might take a minute to do the scan. Then we can see the IP addresses of all of the devices on the network, including the gateway here. But then if we want the MAC addresses, we need to escalate this to an admin level. I'll type in my password. And then it will run the same scan. It might take a few seconds again. And it will return the MAC addresses as well. So you can see the different brands of device that are operating on this network. And then if we pass this through grep with -B2 to capture the lines before, and the string being Raspberry Pi, and then this will filter through and pick out the sets of 3 lines where the last line has Raspberry Pi in it. So there are actually 2 Raspberry Pis running on our network. This is another one on my desk at the moment, and this is the Pi 0 that we are looking to connect to. The IP address can now be used alongside the default username and password to log into the Raspberry Pi via secure shell. On Linux and Mac, the command to do this is SSH, with the default password being Raspberry and the default user being Pi. When you first try and log in, it will ask you to accept the fingerprint of the device, and you just type yes to accept this. The SSH fingerprint is a security measure that is used to verify that every time you're connecting to the same device and not to a different device that is trying to impersonate the one you're connecting to try and steal passwords. So let's demonstrate this quickly. I have a terminal open here and I can type SSH and then the default user at the IP address that we found before. And when I press enter, it will ask me to verify the fingerprint. So you just type yes and then press enter. And then it wants the password, and the default password is Raspberry. Entering that and pressing enter, and then it will log you in like so. So this is now actually a terminal that is running on the Raspberry Pi rather than on our local computer. Once logged in, use the commands sudo apt update and sudo apt upgrade to update the package cache and then to install the updates that are available. This may take some time to complete, but it's necessary to keep everything up to date to ensure that other packages can be installed and used. Now we can use the rpi.gpio Python module to write scripts to control the GPIO pins on the Raspberry Pi. rpi.gpio and Python come installed with Raspbian Lite, so no extra installation needs to be done. For a text editor, we're going to be using the Nano text editor. This is a command line based text editing tool, and to open a file you just type nano and the name of the file that you want to open. To close the file, you press Ctrl X, press Y to save, press enter if it asks you for a file name or type a new file name, and then it will save and close the file. We're now going to look at the pins on the Raspberry Pi and look at creating a circuit which can be controlled from Python to produce a digital signal that can be observed on the oscilloscope. The black numbers on this diagram represent the BCM numberings of each pin. We will instead be using the physical or the board numbers, which are marked in red. The odd numbered board pins are on the inside of the board, and the even numbered board pins are towards the edge of the board. So with this diagram, you'll be looking at the Raspberry Pi holding the GPIO at the top of the Raspberry Pi. The specific pin numbers we'll be using is physical pin 33 for the GPIO digital output, and pin 34 for the ground connection. To generate a digital signal, we'll be using pulse width modulation, or PWM for short. In pulse width modulation, a direct current of a lower voltage is emulated by toggling a higher voltage signal on and off. The frequency of a PWM signal is how many cycles it goes through per second, and the duty cycle is a measure of what percentage of each cycle the signal is at the up position. The circuit we'll be using is very simple. Pin 33 will first be wired into a resistor. The resistor will be connected to a light emitting diode, and the light emitting diode will then be connected to the ground pin at 34. The probe will be connected around the LED, using the provided crocodile clips to connect the anode of the LED to the ground on the probe, and then using the probe head to connect to the cathode of the LED. With the Raspberry Pi set up and the circuit created, we can now begin to write code to perform pulse width modulation. The first thing to do is to open a new file using nano, and I'm going to call it basic.pwm.py. In this new file, the first thing we're going to do is import the rpi.gpio module under the name GPIO. Then, we're going to define a constant called LED pin, which will be 33, which is the physical pin number of the pin we are going to use to perform pulse width modulation. Then we're going to use the GPIO.setMode function to specify which pin numbering mode we're going to be using. In this case, we're going to be using the physical or the board pin numbering mode, so we use GPIO.board to specify that. We can then use the GPIO.setup function to set the LED pin as an output pin on the GPIO. The GPIO module has a function called PWM, which can be used to start pulse width modulation on an output pin at a specified frequency. Here we'll be using a frequency of 100 Hz. The PWM function creates an object which we can use to control the pulse width modulation. Here we do PWM.start to begin the pulse width modulated current. The PWM object also offers a function which we can use to change the duty cycle, which is PWM.changeDutyCycle, and this accepts the percentage that the duty cycle is to be set to as a full integer. Here we use 50 to represent 50%, or the signal being up half the time and down the other half the time. The pulse width modulation will stop once the program exits, so to prevent the program from exiting we'll use an input statement. The input statement will block until the user presses enter in the console. Then, after the input, we'll do PWM.stop to stop the pulse width modulation, and we'll do GPIO.cleanup to free all of the pins so that the next program can be able to use them freely. Now, as before, just press Ctrl X, Y, and then enter to save the file and close it. And now if we use the ls command, we can see the file that we've created here. Now the program can be run by typing python3 basic pwm.py. If you press enter, this arrow should appear in the terminal and the LED should light up on the breadboard.